Okay. So I don't know what's the best thing to do, to continue for half an hour or to stop for 10 minutes. Do people want to stop? People want to have a break? So let me now talk about the other cases that happen. So this is genus 2. In genus 2, basically there wasn't very much choice. It's not possible for this curve to be embedded in P1 because it's a curve of positive genus and P1 has a genus only 2. Right. So for genus greater than 3, then I've got this phi kc taking the curve C to P G minus 1. Right. So here there is a dichotomy So a dichotomy means a logical division into two cases. And we say a dichotomy especially when, if we go in that case, we get a profitable result, and if we go in that case, we also get a profitable result. So this is especially dichotomy is a good thing. It's not a choice between a good choice and a bad choice. So the dichotomy is this. So this is a theorem. Either phi of kc is an embedding, or phi of kc is a 2-to-1 map to P1 embedded as the rational normal curve of degree minus g minus 1. Okay, so from the very beginning of this course, I've talked about the conic P1 embedded into P2 as a curve of degree 2, or the twisted cubic embedded P1 embedded in P3 as a curve of degree 3, not contained in any hyperplane. And the same thing. So this is this is P1 with coordinates uv embedded into P1 with coordinates into Pg minus 1, given by u to the g minus 1, u to the g minus 2 v, and so on. Okay, so the point is here, in either case we get a good result. So here we get the result that the curve is embedded. The curve is not just mapped by its canonical map, but it's actually embedded. And in this second case, we get this very concrete description of the curve, exactly like this, but with 2g plus 2 branch points. So this is I said this is a theorem, so again it's my job to give you a proof. So the proof is again, so given P, Q in C, let's ask Riemann-Roch who is L of Kc minus P minus Q. This is in L of Kc. So this has codimension equals 1 or codimension equals 2. And codimension equals 2 is if and only if Kc separates L of Kc separates P and Q. Right? So this was the condition I had earlier, that I can find elements in here that are 0 on P and non-zero on Q, and conversely non-zero on 0 on Q and non-zero on P. Right? So if this happens always, if this always happens, then so if this happens for all PQ, this implies that phi kc is an embedding. Right? And in the other case, if L of kc minus P minus Q has dimension G minus 1, this is the case where I only had codimension 1, so this is the dichotomy. Either I have this one or this one. If in this case I had this, or, so this implies that L of P plus Q equals 2. So in other words, L of P plus Q defines a map phi of P plus Q from my curve C into P1. Right, and this is of degree 2. So, these arguments are very simple. There's nothing, they're sort of sophisticated, but they're really very simple, technically very simple arguments. Right? I have this result about saying what's the dimension of these linear systems. Right? And so I ask the question, I go down from L of Kc to L of Kc minus P minus Q, what happens? So I know that the dimension, when I take away one point, the dimension must go down by 1, because I proved that over there. So if I take away a second point, what happens? Well, it could happen that the dimension goes down again by 1, and in that case, it means that, that the linear system Kc, this Riemann-Roch space of Kc, has enough functions to separate out P and Q. That's exactly to say that this map is an embedding. Right, and the other possibility is that no, it goes wrong. And then we ask Riemann-Roch, what is L of P plus Q? So exactly as in this inequality there, well, not to write it out again, I would get 1 minus G plus 2G minus 2 minus 2, plus degree of D, and then plus Q minus 2. I'm sorry, G minus 1. So this sort of business about the geometry of the canonical map continues for a while. As I said, I could lecture on it for another 10 lectures if necessary. It's a very interesting subject, and there are several textbooks written. So let me just give. So there's a book by 4 authors: Arborello, Cornalba, Griffiths, and Harris. And so these guys have a 2-volume book in Springer. I think it's university text, but I may be wrong. So there's a lot more of this. I'm not going to pursue this. Let me just pursue this just for one moment more. G equals 3. So G equals 3, the conclusion is either phi kc takes C and embeds it into P2 with the image C is C4 in P2, non-singular quartic. So in this course I've already talked about the non-singular conic and the non-singular cubic at some length. So here's the next case up, non-singular quartic. Or phi kc is C 2 to 1 to a conic in P2. So this conic is P1, and this map is exactly that picture there, but with 8 branch points. So this is C given by y squared equals F8 well, let me just leave this. Okay, so I'm talking about what a sort of pleasant result this is. Let me now talk. Let me talk about the proof of Riemann-Roch, which I have not completely completed, and there's sort of several reasons for that. But let me talk about the material surrounding the proof. So let me talk about the proof, the complex analytic meaning of steps in the proof of Riemann-Roch. So let me go back to this picture, sigma, complex Riemann surface, compact Riemann surface. Right, so it's this picture which I drew. Let me draw a little sort of bit of it a bit bigger, so it looks something like this. So suppose I were to point P. What I want to triangulate this. I want to do something, this sort of basically vulgar topological thing of breaking it up into triangles. Right, triangulate it. Now this is easy. This is, if any of these pictures you find of Riemann surface, you just you do this. I'm not going to discuss this. The reason I want to triangulate it is I want to use Cauchy integral theorem. So if I've got some finite set of points, I've got a function. I've got a function or several functions or several differentials. So I've got a finite set of points here. So I want to take these points like this and then do some argument which is going to take an integral around a contour like this and then around a contour like this. Right, so sigma is covered by triangles. So this is topological. The argument here is in topology rather than in algebraic geometry. And if I cover it by triangles and run this argument here, then every side of the triangle, I'm going down it one way, and then I'm going up it the other way. So if I think of covering every single triangle once, I've gone up every one of these once and down every one of these there. And so the consequence is that a contour integral, if I take the sum of contour integral over all of these triangles, I get precisely 0. So let's think about this thing that divisor of f has degree 0. So how can we prove this? So proof. I want to do integral of around 0 of df over f. Right? So f has finitely many zeros and poles. Right? So let's just take one point P here and take ZP local analytic parameter. Right? Then that df over f is the same thing as df by dz over f times dz. Right, so this is f primed over f dz. So this df over f is something that makes sense. I'm going to talk about it a little later. It makes sense also in algebraic geometry to take df over f. But if I write the f as, I think of the f as being a complex, a function of this complex parameter, then it makes sense to do df by dz. And then this thing here, which maybe has some intrinsic meaning, is written locally like this. So everybody knows that the residue so this has residue at P equals the valuation P of f. Right? Because if f has a 0 of order n, then f is, it means f is z to the n times a unit, then df by dz is n z to the n minus 1 times a unit. Right, I'm differentiating that bit and that and that, and then I'm differentiating the unit times z to the n, but that'll give a higher order term. Right, and so when I do df by dz divided by f, this is n over z plus higher order. Yes, and when I integrate this around, a little path that just goes around the point P, so if I think of just one little path that goes around like this, if I call this gamma P, this is n. This is 2 pi I times n. Let me take 1 over 2 pi I here. Yeah, so the Cauchy-Riemann, the Cauchy residue formula here gives me a method of calculating in analytic terms the degree of zero and poles. Right? So if f had a pole of order n, we get something similar. If f has no zero and no pole, you run the same argument and you find that there's residue 0 here. That's important. Right, so now do the same. Now do the same contour integral. The integral of the same df over f around the whole of sigma. Right. So there'll be some finite number of these triangles which have zeros and poles in them, and then the rest. So here there's I'm doing an integral here, no zeros and poles, no zeros or poles. then when I do this, I get 0. Right? When I do this one, I get the sum of the zeros and poles there. So, it's basically just a simple counting argument. So the contour integral is 0. So I've chosen the triangulation to avoid any of those finitely many points, right? But because we integrate backwards and forwards, along every one cycle, along every edge of the triangulation. Right. So I've covered this. This thing is a manifold, and so wherever there's a boundary here, whenever there's an edge, the edge lies on exactly 2 triangles, and these are oriented paths. This is this statement here about Cauchy's integral theorem is about a counterclockwise path. So I run counterclockwise around each triangle. So every time I go to an edge, I go up it once on the right-hand side, and I go down it on the left-hand side. Right? So I get 0. On the other hand, the thing I get is the number of zeros plus the number of poles. Right, so this is 0, and on the other hand, it's equal to the sum of Vp of f times, it's that. Right, but by this result. So this brings us to the very interesting question of what is Kc. And I'm going to discuss this in algebraic geometry, but first let me discuss it in complex analysis. The Kc is omega c, is differential one forms. So when you do complex analysis in second or third year undergraduate work, you don't necessarily, you think this is a function, and this is dz because when you're writing integrals you always write dz. And you don't specially think of this as being a different object than the function itself, right? But in fact, if I change coordinates here, if I had a different z here, I'd have to write the Jacobian transformation, dz by dw or whatever. And so you should think of this as not a function times this factor dz. You should think of this as being a differential. So this expression is a differential. Right. So let me just proceed with this. I want to say that so what do I want to say? So a one form. So analytic, later on complex, later on algebraic geometric also. A one form, so here complex analytic, is a formal expression it's a formal expression dfi f sigma fi d sigma fi dgi with the formal rules. It's a formal expression and then modulo linearity, C linearity, and Leibniz's rule. I'll explain this a little bit more at the moment. So you should really think of one forms as being something that you already know from Leibniz's rule. So you already know this from calculus. The thing that you integrate is not a function; it's a differential one form. It's a one form. All right. So the set of one forms, the set of meromorphic one, so omega c is the set of meromorphic one forms. the vector space of meromorphic one forms. Right. So at this stage I say that L of the I only want to say one little thing here, which is this: L of Kc plus P is equal to L of Kc. And the reason for this is I'm going to just draw it. If I've got S, so this is F times dz, and this is meromorphic. So Z is a local complex coordinate, local analytic coordinate, and the F is a meromorphic function. So if it when I take the integral around there, so when I do integral around the point P, so this is again gamma P of this S. This is the residue of S at P, residue of S at P. So if I can write this as res P at S. Right, so this is just Cauchy integral formula. So what's this? The thing I'm writing here is I'm taking omega c and I'm allowing a single pole at a single point. Right, so if I take a guy here, S in here, if I take a single element in this omega p, then I can run this same integral now around the whole variety. So if I take S in L of Kc plus P, so this is L of, and this is, sorry, omega c at P. This is a meromorphic form, a meromorphic one form on C with a single pole, with a simple pole at P. Right. So here's the point P and this little contour around it, and then this is contained in some triangle, and I'm going to integrate around there, and then I'm going to integrate around the whole surface. So I can integrate, if I do integral of this form around gamma P of whatever this guy's called, S. This is the residue P at S. On the other hand, I can calculate this integral. I can calculate it equally well by integrating over all the other pieces of the triangulation, right? So if I can integrate now around this triangle and around this triangle and around that triangle and so on all the way around the whole of the manifold. So by arguing on the triangulation, we get, I'm waving my arms now, I'm not giving a rigorous proof, I'm just saying, imagine that I've done this here to calculate the integral, the residue of the form at this point, and then I've done, there are no other poles anywhere else, and then I've just integrated over the whole of the rest of the surface. So over the whole of the rest of the surface I get precisely 0. So we get that this, the integral of S is 0. Right? S has no poles outside, and the only thing that this integral measures is the residue, the sum of the residues inside the triangle. So if there are no poles, the sum of the residue is 0. right? So therefore, S doesn't have a pole. That's all. Right, and so I mentioned that this is the key point of in the proof of Riemann-Roch, and it's you know, we can discuss it in algebraic geometry, but the place the argument really comes from is this Cauchy integral theorem. So so this is a philosophical discussion. I'm no longer trying to worry too much with the details of the rigorous proof of Riemann-Roch. So Riemann-Roch in algebraic geometry. So I do want, however, to make 2 points here, and that is that there's you know, I'm introducing ideas such as the genus of a curve, and these are things that you can really calculate. These are things where there are simple formulas that tell you what the genus of a curve is. So recall from last time that to conclude the proof, I need a divisor Kc with degree of Kc equals 2g minus 2, and L of Kc equals g, and L of Kc contained in L of Kc plus p equals and L. Let me say L of D equals 1 minus G plus the degree of D for all D not all D with L of Kc minus D equals 0. So this is saying, if you think of the Kc as being a positive divisor, this is saying all the guys less than Kc, have some have a strict inequality here, have a greater than. So if the guy cannot be written as being less than Kc, then he's regular, right? Then equality holds. Okay. So the proof I want to give a proof of this in algebraic geometry, and as I explained last time, if C is CD in P2, then then Kc equals D minus 3 times H works. Right? So I explained this last time. I'm taking, so here's my curve of degree D in non-singular, curve of degree D in P2, then, so here's my curve C in P2, and here's the hyperplane section divisor, H. If I took a different hyperplane, I'd just get something linearly equivalent to it. So what do I want to say? I say that we can calculate that the genus of C is D minus 1 choose 2. The degree of Kc is D minus 3 times D, and that's the same as 2g minus 2. And also L of Kc is the number of sections of this. So there's a number of forms of degree D minus 3 on P2. So this is D minus 1 choose 2. And this is G. Right? And we can also see that L of A times H comes from forms in P2, homogeneous of degree A, that this map is surjective. So I didn't, this is the point I slightly muddled. I got it right last time, but there was some kind of Korean folk band outside. Made it difficult to say convincingly. Okay, so this implies this statement here that L of Kc is contained in L of Kc plus P. So this is the place where I'd take, you know, another line and subtract off d minus 2 points, and so on. So I'm not really going to worry too much about this. So that's if the curve is a non-singular plane curve, there is an argument like this. Incidentally, if you want to see this argument done rigorously, there's a little book called Bill Fulton, Algebraic Curves. So it's now Springer. So he does this in very great detail, and he does it completely rigorously. And it's also completely elementary, but just a little bit dry, a little bit boring. So you know, it takes a long time to read this, and but at the end of it you have a completely rigorous proof. Okay, so if C maps to C bar, D in P2 with only ordinary double points, right, so the picture I have here is that here this is CD bar, you know, it sort of goes off. Right, and here is C coming in. So the C has two separate branches that meet up there. So I have a point P here, let's say 2 point P2, Q2. Right, and let me say with delta, let's say delta equals the number of ordinary double points. Then what we're going to do is say the genus is D minus 1 choose 2 minus delta, and the Kc is D minus 3 times H minus sum of this Q1 plus Q2, taken over all the double points. Yes? So I'm changing the rule here. I'm saying the rule is we're going to take D minus 3 times the hyperplane section, just as if it were a non-singular curve, and then we're going to subtract off a little contribution for each of these singularities. Okay? Then you check that the degree is D into D minus 3 minus 2 delta. Right, it's D minus, that's the degree of the first bit, and then each time I see one of these singular points I subtract off 2 points, so that's 2 delta, and this is 2g minus 2. And the L of Kc is D minus 1 choose 2 minus delta. So this is the condition, this is the thing that I'm writing here is forms of degree D minus 3 on projective space that are obliged to vanish at delta points here. So, you know, strictly speaking, I get a greater than equality there, and then we're also at the maximum that can happen, so it's actually equality. And also, these statements analogous to these. Also L of Kc plus P equals L of Kc, and L of AH minus sum of the QIs, so sum Q1 plus Q2 over all P and C, comes from vector space of forms of degree A on P2 with zeros at all the P in singular C. Right, and so this is surjective. It's surjective for all for A greater than D minus C. Right. And so, you know, the argument I gave for this, the argument here, you know, it would not, if I spent an hour on it, I could give a correct proof of it. But it's basically the same as this argument. I sketched out this argument here where I'm, you know, writing down, anyway. So that's not really the point I want to make. So I hope you've seen, I've given you an actual formula for the genus of these curves here. Right? This is something you can easily calculate with. So there is something a little bit strange about this. Because I've told you something, you know, the Riemann-Roch theorem and this divisor class Kc and so on. I've told you things that are intrinsic properties of the curve C. But if you actually want to calculate with them, you have to make some choice. So here I'm making the choice of taking the curve and embedding him in space as a plane curve with ordinary double points. So I can do this for every curve C. This thing here completes the proof of Riemann-Roch if I do it properly. But the point I want to make now is not this calculational point about how we're going to actually prove the theorem, but what does the canonical class really mean? And why is it that we have to do this strange business of actually embedding the curve and using the ambient space? So these linear systems here are things that come from the ambient space. You know, the statements we want to make are all about the intrinsic geometry of the curve C, and we're not interested in the ambient space. But all the calculations here involve the ambient space. So let me just say, so this is definition. So remember, K is an algebraically closed field. And C is a curve. So non-singular projective algebraic curve. So definition, I'm going to write omega C. So this is the space of differential 1 forms of C, of Kc. Yes, I'm sorry. This is Kc over C. So this is, I want to write, this is formal expressions sum FIDGI modulo two kinds of relations, K linearity and Leibniz. Okay, so this is a sort of complicated thing. It looks as if I've written down this is for all Fi Gi in K. It looks like I've written down something impossibly complicated, right? Let me say this again in a different way. This is the universal. This has universal mapping property for derivations. This is a very easy thing. I'm going to explain what it is in a second. For derivations, if I take Kc is a certain field, I'm going to I try to make derivations of it to a K vector space. right? So these are k derivations, meaning they're k-linear. I try to map kc into some k vector space, and to say that it's a derivation just means it obeys Leibniz rule. So d of fg is what you expect, d of fg plus gdf plus fdg. Right, so there's a little theorem here that says if x is in kc, and in characteristic P, x is not contained in kc raised to the power of p. So it's not the piece power of, it's not the piece power. Anyway, you don't need to worry about inseparability at the moment. Right, I'm taking an x here which is not a piece power of an element of kc if I happen to be in characteristic P, then dx is a basis of omega xp, omega kc over c. It's a basis as a kc vector space. So you know, this is really something you already know, because, and I saw it in some of your homework, you know perfectly well how to find differentials when using how to do implicit differentiation. Right. So because this is true, because for all f in kc, there exists a polynomial relation, irreducible polynomial relation, p of f and x equals 0. Right, and then I do df by dp, and this says that f equals something times df is something times dx. And this thing is just obtained by implicit differentiation. Yes? So I'm writing down this grandiose construction in algebra using, you know, the set of all f's and so on, using universal mapping properties. But actually what this means is take an element x here, and I assume that it's I'm assuming here that it's a separable transcendence basis for the field. It means that every other polynomial p, every other function in the field, can be written as a function of x, as an algebraic function of x, also as a separable algebraic function of x. Right? So that's what this is about. I'm not going to explain it. So in other words, this argument I had before with Cauchy's theorem, there we were talking about meromorphic one-forms. So I say there is a perfectly good algebraic analogue of meromorphic one-forms. Namely, it's this space of rational one-forms. And it's just a one-dimensional vector space over Kc. So, you know, when you see a one-dimensional vector space, it's sort of always quite tempting just to choose a basis and say it's the same as the field. X in Kc, and maybe I say non-constant, any non-constant non-piece power. Right, and then if I've got an element S in there, I can define the valuation at P of S. Right, and this is compare S with dxp. Right, so I'm standing at a point P of the curve. I've got this valuation ring OCP, and the valuation ring has this element xp in it. So we're doing algebraic geometry. This is not complex analysis. This guy here is a generator of the maximal ideal of this local ring. So we're just in the theory of discrete valuation rings here. It's nothing to do with complex analysis. I'm taking this element dx, xp, and I'm writing dxp. So this xp, whatever else he is, he's certainly an element of kc. And he's certainly not a piece power. Because if a piece power vanishes once to point, then it vanishes p times, automatically. Right? And then kx, kc is sum of this Vp of s ds. Okay, so I'm not, sorry. P. Right, so formally speaking, this looks exactly like a principal divisor. So it looks exactly like the divisor. This is divisor of S is equal to this, and Kc is the divisor class of any div S. S in omega. Omega Kc over P. Okay. So the difficulty with working directly with this omega c is, we don't know how to calculate with it. The only way we know how to calculate with it is to choose, for example, an element here which is the basis of it, and then say it's a one-dimensional vector space, and then I'm going to compare other differentials with this dx, or choose an embedding in projective space and then and use constructions involving the so we're close here to a subject called duality for projective space. There are several other things here that that would really be for a more advanced course. So I think I've probably gone over time for today anyway, so so it's been a great pleasure to talk to you during this term, and I hope to see some of you back in next January. Any problems with the material? Oh, I have some example sheets to give back to you, some marked work to give back to you, and I want to collect any homework that you have to give me. Can you deal with this? Or can I? Homework?